When you arrived in Munich, Sommerfeld was just working out his quantum theory of free electrons.
Not quite.
Yeah.
When I arrived in Munich, it was 1926.
26?
26.
Ah.
And the big thing was that quantum theory, for the first time, was on a firm basis from Heisenberg and especially from Schrödinger. And Sommerfeld loved Schrödinger's wave mechanics because that was the sort of thing, differential equations with eigenvalues, the sort of thing that Sommerfeld had loved for a decade or two. And he gave a special course for graduate students on the differential equations of physics. And Schrödinger fitted right in, so we all were asked to take one section of Schrödinger and give a seminar on it. And so that's how I learned some Schrödinger's perturbation theory, because that was the section I was to give in the seminar.
But then when he came to applying it to solids...
Now, in 27, a year later, he applied it to solids.
Right, and at that point he decided the electrons could be treated as free.
Well, he was very much impressed by papers by Drude early in the century, in which Drude had used classical mechanics and free electrons. And Drude just assumed electrons must be free. If they are to conduct, they better be free. And Sommerfeld assumed that likewise in quantum mechanics. Neither of them had proved that the electrons indeed were free. That was only done by Bloch about a year later, and only in quantum mechanics. You cannot prove free electrons in classical mechanics, but in quantum mechanics, Bloch proved that the wave function of an electron was a plane wave multiplied by a function which was periodic with the period of the lattice. And Bloch, in a way, was the fundamental origin of the free electron picture.
So Bloch, in a sense, vindicated Sommerfeld.
Right.
Yeah. Were you suspicious of Sommerfeld until Bloch?
Not at all.
Why not?
I came from a slightly different direction. I was told by Sommerfeld for my thesis to make a theory of the experiments of Davison and Germer, which proved the electron, the wave nature of electrons, and proved that electrons behaved very much like X-rays. And so it was obvious to me that electrons were free.
Uh-huh. Was Sommerfeld worried about, for example, the anomalous Hall effect, which is
I
a
don't
real
be-
challenge for
I
free
don't
electrons?
believe so. But he was happy to see it explained.
Uh-huh. Yeah. I found a nice quote from Piles, actually, about Sommerfeld in the context of free electrons. He says, it was characteristic of Sommerfeld's positive attitude that one learned more about the successful solution of difficulties than about the mysteries that remained. He was completely fair in listing the contradictions. It was just a matter of emphasis.
This is a very good description. Pius and I were simultaneously graduate students with Sommerfeld, and Sommerfeld indeed emphasized the positive.
Mm-hmm. Do you remember what Sommerfeld's reaction was to Bloch?
I don't remember. I don't remember, in fact, that Sommerfeld was worried about electrons being free,
Uh-huh.
and but to me, Bloch was essential.
One of the things that always struck me about Bloch's work was that, first of all, he showed that electrons in a periodic lattice behave like free particles with an altered energy momentum relation.
Yes,
And then immediately, people studied the response of such electrons to applied electric and magnetic fields by treating them as classical particles with that altered energy momentum relation. Now, showing that you can do that is not so simple.
yes.
Was this controversial, or was it regarded as obvious, or what?
Well, physics was simple in those days, and it was obvious you needed free electrons to have conductivity.
Right, but I mean, once Bloch had shown that electrons did propagate freely,
Yes,
it was clear there were free electrons. But then you want to know how they behave in magnetic fields, for example. And Piles assumed that they would be acted on by the ordinary Lorentz force, the only difference being the velocity was not proportional to the wave vector.
yes.
And that, in a sense, is a big leap from
It may be a
Bloch's theory.
big leap, but at that time it seemed obvious.
Uh-huh.
Electrons are acted by a Lorentz force.
So this funny use of quantum mechanics to get the
Yeah.
altered energy momentum
Yeah.
relation, and then you start being classical again,
Yes,
was fine.
right.
You know. And of course, it worked.
It worked. It seemed obvious that that's the way to do it.
Mm-hmm. What about the question of electron-electron interactions?
Ah, thank you. I understand that the Russians found that very difficult. But to me, it seemed quite obvious because, after all, it happened in an atom. And we had the Hartree-Fock theory of electrons in an atom, So we obviously would have a Hartree-Fock theory of electrons in a crystal. And I think it is very strange that the Russians found it difficult because, after all, Fock had told them how to use electron interaction. Hartree already had told them. And I found it quite natural to treat electrons by the Hartree approximation, and the Hartree approximation simply said what you said a moment ago, namely they behave like ordinary electrons with a different relation between energy and momentum.
The Hartree-Fock, yeah.
And it was obvious that the Fermi surface had to be a sharp surface, otherwise you wouldn't get the Fermi distribution.
Over the weekend, I found a statement from Bloch, who said it worried him, the neglect of
Yes.
electron interactions. But he felt it was worth seeing how far you could get in a one-electron picture.
Very good. It didn't worry Pius and me. Pius and I worked very close together. We had been graduate students in Munich simultaneously, and we stayed together by letters ever since. And we didn't find any difficulty.
Of course, eventually it did become important for questions like metal insulator transitions.
It did indeed, and the great person there is Neville Mott. But we did know that there was a Fermi surface in reciprocal lattice, and that Fermi surface would not necessarily fit into an elementary cell of the reciprocal lattice.
Yeah, that brings us to the question of the distinction between metals and insulators.
Right.
And
It was perfectly clear to Pius and me that insulators were substances in which the band was completely filled.
apparently it wasn't obvious to Bloch as late as 1931 because he says in a 1980 retrospective article
Yes.
in Procroy Sock that, what does he say now? That the band theoretic basis for the distinction between metals and insulators he did not understand until it was pointed out by A.H. Wilson in 1931. And he actually refers to my misconception of the essential difference between insulators and conductors, later pointed out by A.H. Wilson.
Well, Pius and I believed that we understood it perfectly well. An insulator had completely filled bands, and On the other hand, the elementary cell of the reciprocal lattice in general did not coincide with the Fermi surface, and that made it possible to have divalent metals where part of an elementary cell was empty
Yeah.
and part of the next band was filled.
But, you know, apparently that had not occurred to Bloch as late as 1931, because both Bloch and Wilson independently tell
Yes.
this story of Bloch not believing Wilson
Yeah,
when he made this point. Apparently Bloch believed that it was a continuous difference. It was a question of the tunneling probabilities getting very
Sure.
small.
so it seems.
And
We did not correspond with Bloch in those days. But Pius and I were very impressed by Brione's reciprocal lattice. And there are pictures in my article with Sommerfeld, which shows that by 1933, certainly, we had understood it completely.
well, Peierls in that same issue of the Proceedings of the Royal Society
Yeah.
Asks himself the same question: when did we realize the band theoretic basis for the distinction?
Yes,
And he says that in his 1929 Hall effect paper,
yes,
there is the statement that a filled band will not conduct.
yes,
But he does not expand that into a discussion of the fundamental difference between metals and insulators.
that's correct.
My guess is that the reason he didn't was that he was very strongly focused in that paper on conductors.
Yes,
And then he went on to talk about nearly free electron systems,
yes,
the opposite of tight binding, where, of course, everything is metallic. So it sounds as if in a sense, Wilson may have been the first person explicitly to raise that question
I think that's correct.
and say, what is the difference?
Yes. But it was clear to Pius and me.
One of the things Peierls did do explicitly involving insulators was the theory of thermal conductivity and
Yes.
the importance of Umklapp processes.
Yes. Now, Umklapp processes were important already for metals because, after all, when you have resistance, you have an interaction of an electron with a lattice wave. And the sum of the wave vector of the electron and the lattice wave could very easily go beyond the limit of the band, of the Brillouin and so on. And therefore you needed Umklapp processes already in metals
To have a resistance.
to have a resistance,
Yeah.
especially at low temperature, but even at room temperature. The Fermi surface of sodium is almost a sphere, which doesn't fit into the reciprocal lattice. So if you had resistance, you had to go from one side of the Fermi sphere to the other side. And you could do that only by lattice wave of considerable wave number.
Mm-hmm.
So Umklapp processors were immediately needed already in metal resistance.
Right. As I
Nobody emphasized.
As I remember, Peierls also made the point, maybe it's the same point in a different language, that without Umklapps, the electrons and the phonons would come to equilibrium together, but in a moving frame.
Correct.
So
That's
that,
exactly right.
right, which Bloch had avoided
Yes.
in his early paper by
Yes.
putting in by hand
Yes.
that the phonons were already in
Yes.
equilibrium in the stationary frame.
Right.
So the notion of Umklapps was also not controversial. People
Yes.
accepted
But
it.
the application to heat conduction in insulators was extremely important and gave a very remarkable result. Insulators conduct heat better than metal at low temperature.
I don't think that was actually observed for another couple of decades. I think it
You're
was,
right.
I think it was only in the early 50s that people made crystals pure enough.
It was observed only 20 years later, because only then could people make pure enough substances so that the Umklapp processor had any meaning.
In fact, I found an amusing remark of Peierls to the effect that he had failed to warn people that the crystals had to be not only chemically pure, but isotopically pure as well.
Yeah.
And that apparently caused some confusion.
I don't remember that.
Yeah, but it makes good sense. If you
Yes.
have a mass
Very
variation,
good
that will,
sense.
yeah. Pauli is said to have been fond of saying that he invented solid-state physics.
Pauli, in fact, wrote the first paper in which quantum mechanics was applied to crystals. And he explained paramagnetism of alkalis by this means. And that was important. It may even have influenced Sommerfeld,
Yeah,
but I don't know. But the important part of solid-state physics is that you have the whole solid state and not just one atom in the solid state. And Bloch had only considered one alkali atom in the solid state.
But aside from paramagnetism, did Pauli do any other work?
No, and he despised solid state theory. In fact, he said he had wanted to take me as an assistant, but I worked on solid state, and he didn't like that.
I wonder why he didn't.
I do not know, and I never asked him.
In thinking about this conversation, I'm ashamed to say that for the first time in my life, I actually looked at your long article with Sommerfeld on the electron theory of metals. And I was struck by how big it is. I mean, it makes a 300-page small print
Yeah.
book. And the other thing that struck me was how much duplication there is between your 1933 book and my 1976 book with Neil Ashcroft on solid-state physics.
Well,
How much
that
was already known in
shows the stability of the
Right.
theory.
Yes. But the final thing that struck me was it took me and Neil, how long? 8 years to write our book. And I believe it took you,
It took me 1 year.
yes, and the question is how? Why did it only take you 1 year to write such a massive?
Well,
Compendium.
there was a lot less known at the time, and it was very close to our daily work.
But that book is almost 300 pages, a very
Yes.
small print with many figures, and I presume you were doing other things at the time.
Yes, I was, by that time, my real interest was nuclear physics,
Uh-huh.
which started with Chadwick's discovery of the neutron in '32.
Are you the kind of writer who can just write things once and it's perfect? Does it just
I
flow?
was at that time.
Uh-huh.
A friend of mine, George Platschek, claimed that I just had 2 stacks of paper. One was white, and the other I had written on, and I wrote continuously and turned it over to the other pile, which had the finished product. Fermi worked the same way.
And in addition, I assume you didn't sleep very much.
Fermi didn't sleep.
No, did you sleep very much?
Oh, I slept a great deal.
Really? I'm very impressed.
8 hours a day.
I noticed that there's a footnote to chapter 1 by Sommerfeld saying that he wrote the first chapter on free electrons, which is 35 pages or so, and that you wrote the rest of the book. Nevertheless, the book is Sommerfeld and Beta, and not
Yes.
Beta and Sommerfeld.
Well, Sommerfeld was a famous physicist who could do almost anything he wanted, and he was on very good terms and very well regarded by foreign physicists. They all invited him. He was a lecturer at Ann Arbor in the summer school. He was he got the premium of the American Association for the Teaching of Physics, which is
For those wonderful books. For those wonderful books of his.
one of the,
Yeah.
yes. And I was very proud 20 years later when I got it.
Uh-huh.
Sommerfeld was known all over the world. So in order to show that this is a serious book,
Uh-huh. Right.
Sommerfeld had to come first.
Uh-huh. Uh-huh. Yes, I think things have changed somewhat. I think these days the student's name tends to come first, if at all possible, if it's a collaboration.
to advertise him.
Exactly. It's been terrific talking to you about this.
It
Really?
was
I've learned
it
a
was
lot.
fun.
It was indeed.